Today, ladies and gentlemen, we will start Chapter 6. 6.1, Slope Fields and Euler's Method. Now, the first lesson we need to have is a very short and simple one, but important one nonetheless, is the correct pronunciation of this word right here. Please do not pronounce it Euler's Method. It is called Euler's Method, named after the famous mathematician Euler, whose picture is hanging in my room if you want to come and see him at some point. But today, ladies and gentlemen, it's applications of differentiable equations. We're going to use those to sketch slope fields and also, again, Euler's methods, which you'll see when we get there in just a moment. Alright, and while we're waiting on it to come up, let me back up a little bit. There we go. Differential equation. Equation involving a derivative is a differential equation. Perhaps you have heard in the past some of your college friends or perhaps relatives refer to the infamous DiffEq class. Well, this is a math class completely devoted to differential, that's the diff, equations, EQ, DiffEq. But it's simply an equation that has derivatives and higher derivatives and non-derivatives all mixed together in one. And our goal today, one of them, is going to be to solve those equations. For example, dy dx is secant squared x plus 2x plus 5, and we are going to solve this equation. How do we do it? Well, first of all, we need to think about a way to get rid of the dy dx. How do we get rid of the dy dx? Well, that's very simple. To get rid of a derivative, you will do the antiderivative, or the integral of both sides. Alright, well, the antiderivative of this, the antiderivative of the derivative of y, would just be y. What is the antiderivative of secant squared? That would be tangent x. The antiderivative of 2x would be x squared. The antiderivative of 5 would be 5x. Let me erase all that, and we'll bring up the actual neat writing where you can see it a little better. Right there. And then don't forget, we always do plus c. Now, this is a very simple differential equation, but you see the idea. It involves regular x's and it involves derivatives also. Now, we will later on actually throw in some more complicated that have second derivatives, that have mixtures of derivatives, that involves different ways of solving a derivative as we go throughout the chapter. First order differential equation. If the general solution to first order differential equation is continuous, that's important. If it is continuous, then, that's a typo there, then only one additional information is needed to find a unique solution, and that is a single point, which we call the initial condition. A differential equation with an initial condition, sometimes called an initial value problem. It does have a unique solution if this is the case. So essentially, here's what's happening. We've done these in the past. We've solved the antiderivative or the integral problems in the past where we have the plus c part. But then I would sometimes give you that initial point that you would plug in and use that to find the c value. Well, that's what this is talking about here. Alright, find a particular solution to this equation. So we'll start with the equation. Let's find the general solution first, the plus c solution. So again, I've got to get rid of the dy dx. I'll take the antiderivative of both sides. So I'll have a y over here, but what is the antiderivative of e to the x? Well, that's just e to the x. What is the antiderivative of 6x squared? That would be 2x cubed over 3, and then we put in our plus c. Now we take our initial point, 1, 0, and we plug that in. 1 for x, 0 for y, like so. And now we solve. That would be, of course, e. That would be 2. And if we solve for c, then c is going to equal 2 minus e. And then, of course, we should always go back and rewrite that in the problem. So e to the x minus 2x cubed, instead of plus c, we'll put our plus 2 minus e. Alright. Another example, same kind of problem, just throwing in a little trig with this one. dy dx is 2x minus secant squared x. Again, same kind of situation. We start out by asking ourselves, what's the antiderivative? The antiderivative of 2x is x squared. The antiderivative of secant squared is, as we mentioned earlier, tangent plus c. To find the c value, plug in the initial condition, 0 for x, 3 for y. We have that. Now that's obviously 0. The question is, what is tangent of 0? Well, we know from our beloved unit circle that tangent of 0 is 0. So c equals 3, rewrite the problem with the c value plugged in. No. There we go. Sorry about that. Now some problems can be written a little differently. Instead of the dy dx, they may have f prime of x, but you see it's still the same kind of problem. The problem with this one is, though, I don't have an easy antiderivative of e to the negative x squared. Well, in the last chapter we studied a way to get around this, and that was the fundamental theorem of calculus, where all we have to do is put the integral sign in, like that. We go from 7 to x. Remember, we do 7 because that's the x value. The corresponding y value should be 3. Well, this, if you plug in 7, is 0 right here. So to make it a 3, I have that right there. Now, did I actually come up with the antiderivative? No, I didn't solve it out completely, but I solved it enough to where I could. This would be a satisfiable answer on the AP exam. Graphing a general solution. Now, what we're doing here is we're setting up the idea of slope fields. I want you to graph the general solution to cosine x. Well, what is the antiderivative of cosine x? The antiderivative of cosine x is sine x plus c, right? So how many graphs can I make out of it? Well, I know what the normal sine graph looks like. It starts at the origin, goes up, down, up, and repeats itself over and over. But what if a c is 1? Well, then I take that same graph and I move it up 1. What if c is 2? Up 2. What if c is negative 1/2? It moves down 1/2, and so on. So in general, what would the graph of all these sine functions look like together? Looks like this. Here is sine, there's a c value of 1, of 2, of 3, negative 1, negative 2, negative 3, and so on. Notice how the graphs follow the same kind of direction throughout. Now, slope fields that we're about to introduce don't always do that, but this one will. What is a slope field? I'm going to move the screen down just a bit. If I can grab it and move it. There we go. Slope fields, as you see, look very, very confusing, perhaps. Got all these little line dashes in, and what in the world do they all mean? The differential equation gives the slope at any point xy. Again, we're going to have an equation with the dy dx in it. This information is then used to make small pieces of linearization. Linearization, if you recall from a couple chapters back, is where we take and we make a little straight line, like a tangent line at a point, that approximates the solution curve that passes through the point. If we repeat this process at many points, what we end up with is called a slope field. Let me give you an example. All right, here we have cosine x again, and we're going to do a slope field. Now, I don't have my graph labeled here, which I should, but I'm doing a trig zoom here, so this first line here would be pi over 2, and that's pi, and 3 pi over 2, and 2 pi, and so on. So I'll start with pi over 2, and I ask myself, okay, if cosine is pi over 2, and it's pi over 2 all up and down this line right here, if cosine is pi over 2, then if x is pi over 2, what is cosine pi over 2? Well, I know from my unit circle that cosine pi over 2 is 0. Well, what does the slope of 0 look like? It looks like a horizontal line. So now notice I'm putting all these horizontal lines on my graph, but I don't draw them real long. I just make them little small short pieces. So I go to the next part. Alright, I go, that's pi over 2, this is pi. What is cosine of pi? Well, cosine of pi, sorry students, we had to pause for a second. You heard the door open, somebody walked in, it's hard to find a good quiet spot in the building. But anyway, what we were saying, cosine of pi, if you think back to the unit circle, cosine of pi is negative 1. Now, what does the slope of negative 1 look like? It's going to, go have a negative diagonal going down. Looks kind of like this. And again, notice I draw them all up and down because that entire vertical area there is pi. All right, I go to the next part. If that's pi over 2, this would be 3 pi over 2. What's cosine of 3 pi over 2? Cosine of 3 pi over 2 goes back to 0, so I go back to horizontal lines. And then I come back here. This would be 2 pi. What is cosine of 2 pi? Cosine of 2 pi is 1, so I draw a slope of 1. And now if I take these, I can repeat the process at 0. Cosine of 0 is 1. Cosine of negative pi over 2 is 0. And keep going. Cosine of negative pi is negative 1. Cosine of negative 3 pi over 2 is 0. And then cosine of negative 2 pi is 1. Now that may look like a lot of jumbled mess to you, but here's what I want to show you. If we start at any point, say maybe right here, at this point right here. And if we kind of follow, now by follow I mean follow the slope and then go to where it tells you to go to the next point. So I see this one's going up and it tells me to go here. This one tells me to level off and then down, down, level off. And if you see, what you end up with is the sine graph. And that's actually the graph that we had just a few minutes ago. So that is a slope field. Now, on this one, all I had to do is plug in x's because x was up here by itself. Is that always the case? Absolutely not. Sometimes you have x's and y's. Like this one. This one wants me to construct a slope field for x plus y. And then it wants me to use that slope field to find a particular solution that passes through the point 2, 0. Now, I've actually given you this graph on your paper so that you can sketch that slope field yourself, just to give you an idea how it's going to work. For instance, right here at 0, 0, the origin. On the origin here, if I plugged in 0 for x and 0 for y, I get a slope of 0. So I would come here and I would put a little slope of 0. But now I wouldn't do that going all the way up and down because this depends on x and y both. Here, it's x is 0, y is 1. Well, 0 plus 1 is 1, so I'd make a slope of 1. This one would have a slope of 2, so I'd make it a little thicker, so obviously I'm not doing a good job drawing. Down here would have a slope of negative 1, and of negative 2, and then so on. This point right here, which is 2, 2, would have a slope of 4, almost straight up and down. And we would just keep doing that and making our sketches, and in the end, let me erase that. In the end, we end up with a graph that looks like this. Now, it tells us next to sketch the particular solution that passes through the point 2, 0. So I find 2, 0, which, maybe 2, 0 is about right here on my graph. And I find the lines that are closest, and I'm looking right here. You see these lines right here. Do you see how the shape that they follow right there? So what I would do is I would start at this point and I would kind of follow those shapes along, and in doing so you end up with that graph right there. So apparently 2, 0 was over here, based on their scale. So there's 2, 0, and you see this what they've got right here going along the graph. Alright, now one of the things that the AP exam likes to do, for those of you that are still considering it, and I hope many of you are, is they like this kind of problem. They give you a variety of functions here, and then you have to match which differential equation goes with which one. Now, having said that, ladies and gentlemen, I am going to be putting a slope field function on your calculator. In fact, I've already got the program on there. I will, when you come to class, show you how to use it. In the meantime, the way you would do this is you would find random points. You just pick random XY points, plug them in, and then based on those XY points, make your slope fields, and certainly pick some on the axes, pick some in each quadrant, just to kind of see what the lines are doing, and then based on that, you'll be able to pick out which one matches what. So if you want to do that yourself right now, go ahead and pause it. I'm getting ready to give you the answers. So this first function here matches up with letter B. The second one goes with D, the third one with A, and then the fourth one goes with C. Now for the favorite part of the lesson, at least my favorite part, Euler's method. Euler's method, ladies and gentlemen, is a way to approximate function values if you don't have the function. If you just have a differential equation, just the derivative, dy dx, you can use that to describe what the function is doing without actually obtaining the function by means of an antiderivative. Okay? There's a lot of stuff here, and certainly pause it and read over this if you want. Best thing to do on Euler's method is to just jump straight into a problem. Now, before I do that though, we're about out of time on this first section of video, so I'm going to go ahead and wrap up this first video, and then when we start the next one, we'll start on the next slide.